Next up, the next speaker is Matthieu Durnerin. Did I say it right?
Yes.
Okay, I practiced. Good. Matthieu joined STMicroelectronics in 2002 with a background in telecommunication and a PhD in signal processing. After leading several different activities on cellular telecommunication, audio, sensor hub, and machine learning, he's now the head of the Artificial Intelligence Applications, Algorithms, and Tools team in the Microcontroller and Digital ICs group. And today, Matthieu will tell us about making it easy to optimize and deploy tiny machine learning on STM32 microcontrollers.
So, hello. Indeed, in this presentation, I will present you an overview of our solution to implement easily some neural networks on our microcontroller STM32. So smart objects are changing nearly every aspect of our daily lives, and microcontrollers can be considered as the brain of these smart objects. Machine learning is not a new technology for sure, but it's only recently that it has become so disruptive and more applicable. Some initiatives like the one that I will present and, for instance, Tensor Flow Lite for microcontroller, already proven that microcontrollers have sufficient processing power to run neural networks. And with all the advantage well known to run them locally. So the core component of our solution is STM32 Cube.ai, which is an extension of our more generic tool, CubeMX, which is a tool that allows to configure our STM32 and generate some code. And Cube.ai is a conversion tool, so it's taking into input a pre-trained neural network and convert it in optimized C code that will take all the advantage of hardware and software implementation related to microcontroller and provide a very optimized code. You can take into input different formats. So you have all the standard deep learning framework, Caffe, Keras, Tensor Flow Lite, Lasagne. And we recently also added the support of ONNX, which means that all the frameworks that can import, export to ONNX can be supported by extension by the tool. On top of this, what we are providing is what we call a function pack. It's some software example, end-to-end software example. So you have low-level driver, you have middleware, you have pre-processing, and then some neural networks that has been generated thanks to the tool that are providing this complete example. So we have this first pack called HPAI Sensing one, which are providing two examples, one on human activity recognition and the other on the audio scene classification. And on this example, you will not find only how to run the inference, but we are providing some additional feature. For example, on this pack, it's very easy to label, to gather the data, to acquire the data and label them for further learning. And it's working with a companion app on BLE. We have another function pack, which is called the FPI Vision 1, which is focused on computer vision, this one. It's featuring food classification, able to recognize 18 classes of common food. But it's only one example. It's really the ground to build your own application and to do furthermore kind of image classification. It could be default analysis, person detection. It's really a lot of use cases that you can do with computer vision. Here, it's the flow to use our solution. So the first step is to design the neural network. We are not designing it. Our customer data scientists use the standard framework they prefer, so Tensor Flow Lite, whatever. And once they are happy with the network, it's pre-trained, it can be imported easily into the tool that will generate this optimization. So the tool is not only generating, it's providing also some additional feature, like the support of the quantization, but also some optimization, like the weight compression. So a few features that you can test to improve, at the end, the support of your neural network. And then you can also validate. So we are providing some way to validate the optimization. Of course, it could be an iterative cycle. And at the end, you use the function pack to integrate your generated code into a full example and to derive very quickly a functional proof of concept. So here it's a snapshot of our tool. So if you are a little familiar with our ecosystem, you recognize the UI. It's really fully integrated in CubeMX. So it's a standard UI from CubeMX. And so it's very easy to analyze a network. So you enter the model here. Here's the float Keras H5 model of the food classification. Then you can display here. You press the show graph, and you see the topology of the network. Here it's a convolutional network. And then you can press on the Analyze button, and that will give you a lot of information already on the multiplier I accumulate, the memory used by layer, each layer of the neural network, and of course the total number of memory used. So in this case, for example, we have, after analysis, more than 1 megabyte of RAM that is used by this model. The question, and it's not fitting in the targeted STM32 that we want to select. So how to reduce it, typically? So one of the ways to use quantization. So I assume that everybody is aware of what is quantization here, but just to in case someone doesn't know, it's really the operation to convert 32 bits float model into quantized models. And here we are talking about 8 bits. We are not supporting lower kind of quantization. At the end, you will reduce, of course, the model size, the memory usage, but also by taking advantage of the DSP instructions of the Cortex-M, you will also reduce the latency, so the inference time. We are regarding quantization, we are supporting different kind of quantization. We are supporting the quantized post-training quantized model from Tensor Flow Lite converter. So the output of the Tensor Flow Lite converter, it is taking into input a Tensor Flow or Keras model and transform them in an 8-bit quantized model. But we are providing our own quantization scripts, adding a little more option in terms of quantization schemes and different options. We can support also Tensor Flow Lite quantized aware trained models, so meaning models that has been quantized during the learning phase, so that can take advantage of knowing the quantization, of taking into account the quantization noise. Then you can easily validate your model, quantized or not, by the way. You input your model, but you can input also some data. So you can use either random generated data, but we encourage to use directly the validation, your dataset, your own dataset. And then you can just press the validate button, and we have two options. We can validate on the desktop directly, or you can simply plug STM32 board, and the validation will be done directly on the board. And that will give you, if you use the board, we will also provide then the inference time, the megahertz used. And at the end, you have all the details, including the confusion matrix in case of a classification issue, and if you have provided the data set. And you have all the details on every layers, and it's very important to understand the outcomes of the optimization, so you can check that you, for example, you don't degrade the accuracy. For instance, if you have used a quantized model, but also where are the bottlenecks in your networks, because you have all the information by layer. So here is a few results of what we can expect when we go from a float model to a quantized model. So we use, again, our food recognition example on our high-performance STM32H7. So you see here you have the float model, and the gain is we divide almost by 4 the memory usage, the flash and the RAM usage. And the accuracy, the inference time is divided by almost 3 in the process too. There is another advantage here. The RAM was not fitting in the internal memory. And then with the quantized model, everything is fitting. So the improvement in inference time is due mainly to the quantization, but also to the fact that we are using internal memories in this case. So the H7 discovery board that is running the FPI Vision 1 is embedding some external flash and external RAM, so to provide more flexibilities and more options. So, for instance, you can support a camera with higher resolution, but also it's very important you can support some neural network with more complex, so more weight. It's also very important to check a little this different configuration. So you have a way to put either the weight in external flash or in external RAM. It's very configurable. So we are providing the way to split the weight. You could put them in external flash. You could put the activation in external RAM and so on. So this allows to really check the different compromise, memory compromise, and the impact at the end on the inference time. Here, typically, it's an example of what the gain we can have using external memory or internal memory, again with your food recognition example. And that you see especially on the float model, where the weight more, the size of the weight is more important, that we divided almost by 2 the inference time by using internal memory. So that's the kind of gain that you can have using internal memory compared to external memory. And you have to consider that using cheap and low-cost external memory can also increase this difference. And the more weight you have to fetch from the external memory also will impact the inference time. So using external memory can come with a very high cost. Another approach to support neural network on microcontroller is a Tensor Flow Lite for a microcontroller. So here I just give you an overview of the main difference between the two approaches, QBI and Tensor Flow Lite for microcontroller. So first, apart the fact that we are supporting more directly more network, deep learning network framework in input, the other difference is that Tensor Flow Lite for microcontroller is an interpreter. So the library is built on selected operators, and you can have also a custom operator. And then the flat buffer that is representing the topology and the weight of the network can be copied directly on the RAM and is interpreted at runtime. You don't have to link it to the other user file. On the other hand, with QBI, everything is done offline. So we are importing, analyzing, optimizing the network. We are generating some C code that we'll call a pre-compiled library. And everything is built at link time, at compile time, which allows to embed only the needed code, so only the used operator. Another difference is that the flat buffer here need to be located in a single memory chunk, whereas we have a way to split the weights in different memory locations with QBI. And then a few results we compared. So it's a recent snapshot of QBI against TensorFlow Lite for microcontroller. We use a percent detection example that is part of TensorFlow repository. And we ran the 2 comparisons, one on the ultra low power microcontroller, the L4R here, another one on our high performance microcontroller. And you can see that on both cases, the main gain is on the inference time, where we divided by almost 4, but we gain also on the flash and RAM size. Flash is mainly it's only the weight and the topology, so the flat buffer comparison. At the end, we gain obviously on the power consumption too. So as a summary, we are not proposing only an optimized tool, a conversion tool. We are proposing a full ecosystem. So including the tool itself, the function pack to easily derive some prototype and some proof of concept, at the end some product. And but it's also a community, so we put in place a community where people can exchange on the forum, and we also have a full network of partners. These partners are knowledgeable on our devices, on STM32 and on AI, so they can help our customer to build their end solution. And we have some other partners that are adding some additional feature, additional solution on machine learning that allow us to cover a very large range of machine learning approach. And that's it. Thank you. Thank you for your attention.